Welcome to How to Use Kubernetes, running Spark on Kubernetes. My name is Adam Harwain. I'm a software engineer working at Google, in particular on Google Cloud. A quick overview of what we'll cover. First, we'll have a brief introduction to Spark and Kubernetes. We'll talk about the different Spark cluster managers, discuss why someone might choose Kubernetes above the other cluster managers, the Spark on Kubernetes operator, Dataproc on GKE, and finally, some conclusions to wrap up. Apache Spark is a multi-language engine for executing data engineering, data science, and machine learning on a single node, machines, or clusters. It is one of the most popular frameworks for data analytics in the world, and is the leading way to do computation over massive data sets. Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications. It has become the de facto standard for running software that can easily migrate from on-premise to the cloud and between different cloud providers. Kubernetes is designed around an extensible, declarative API. Each object in the API represents the desired state of the world. The machinery continuously works to make the world match the desired state. Now we'll talk a bit about the different cluster managers that Spark supports. Cluster managers are the abstraction used by Spark to control where computation occurs, allocating resources across applications. As of Spark 3.2, there are 4 supported cluster managers. The first is standalone. It's a simple cluster manager included with Spark that makes it easy to set up a cluster. It is often used to run Spark applications on a single machine, such as locally for smoke testing a new application. Apache Mesos is a general cluster manager that can run Hadoop MapReduce and service applications. However, the Spark integration with Mesos Cluster Manager has been deprecated and will be removed in a future Spark release. Hadoop Yarn is the resource manager created by the Hadoop project. It runs applications across many nodes. The Hadoop Yarn Cluster Manager is the most commonly used non-Kubernetes Spark cluster manager. Kubernetes, as mentioned before, is an open source system for automating deployment, scaling, and management of containerized applications. Let's look at examples of what it looks like to submit work to different cluster managers. To submit to a standalone cluster, the master parameter is given as a URL with the Spark protocol and the host and port of the master. Across all of these examples, we will be using the same deployment mode of cluster, the same name of the application, SparkPy, the same class, and the same instance. The only things that are going to change will be highlighted, in this case, the master parameter. Similarly, to submit it to a Mesos cluster, the master parameter is given as a URL with the Mesos protocol and the host and port of the Mesos dispatcher. Unlike other cluster managers, in which the master's address is specified in the master parameter, in Yarn mode, Spark will read the address from the local Hadoop configuration. Thus, all that is needed in the master parameter is the keyword yarn. To submit to a Kubernetes cluster, the master parameter is given a URL with the K8s protocol and the host and port of the API server. In addition to the master parameter, we also need an additional parameter to specify the Docker container to use. This is the container that will be used by the Spark driver and executors. Thus, it must have Spark installed along with any other desired dependencies, for example, data connectors or Python libraries. There are other cluster managers. Why would I choose Kubernetes? One huge advantage of Kubernetes is that every application is containerized and isolated from all the others. This allows us to package an application with all its dependencies. Being containerized means that we can have the same experience in development and in production. As each application is completely independent, we can run different applications with conflicting dependencies on the same cluster at the same time. This allows us to use the same hardware for conflicting applications, allowing us to save money by not requiring independent clusters for each set of conflicting dependencies. In addition, many enterprises are standardizing on Kubernetes for all workloads. By moving your data analytics workloads to Kubernetes as well, it lowers the administrative overhead of running them, as well as better ensuring they meet the security and policy requirements of the organization. Finally, Kubernetes ecosystem is gigantic and only getting bigger. Many pieces of functionality are available in mature, open source packages. For example, if you need metric scraping and analysis, Prometheus is very popular. Grafana can be used to visualize those metrics and other data. If logs need to move to some central location, then FluentD is an efficient way to do so. A service mesh such as Istio can be used to ensure network access is restricted to exactly the endpoints that are needed, not others. For example, Spark executors may only be allowed to communicate with their owning driver, not other drivers in the cluster. As we already discussed, Spark Submit is capable of using Kubernetes as its cluster manager. So why would we need anything more? Well, Spark Submit works well if you are submitting from your local machine. However, it is not as useful in an automated pipeline because it needs to run a process locally and by default will wait until the application finishes before exiting. Thankfully, there are more idiomatic Kubernetes ways to run a Spark application. Before I describe those, let me explain the concept of a Kubernetes operator. Kubernetes operators are a framework for adding capabilities to Kubernetes. They have become the idiomatic way to add functionality to Kubernetes. Operators install new resource types into the Kubernetes API, and then they are responsible for acting based upon resources of those types. The Spark on Kubernetes operator is an open source Kubernetes operator that allows Spark to run on Kubernetes in a Kubernetes native way. Rather than running Spark Submit, you'll create a Spark application resource via the Kubernetes API. The resource represents a single Spark application and is run until completion. On the left is the Spark Submit we saw earlier. It is sending the request to a Kubernetes server. On the right is the YAML for the equivalent Spark application resource that would be used by the Spark on Kubernetes operator. They have very similar settings. Let me add some highlighting to make the similarities easier to see. Both require setting the deploy mode, the main class to use, as well as its jar file, the number of executors, and the container image to use. As you can see, the same values are used in both. The Spark on Kubernetes operator works by defining a Spark application resource type and installing a persistent piece of software called a controller that watches for Spark application resources. Whenever it sees a Spark application resource, it will then launch the corresponding Spark driver pod. If the operator is installed with its optional mutating webhook, then it can configure properties not directly supported by Spark itself. For example, Spark 2.4 does not support mounting arbitrary volumes or setting pod affinity. The Spark on Kubernetes operator with mutating webhook would allow you to make customizations even when running a Spark 2.4 application. Next, I will discuss Dataproc on GKE, the project I'm currently working on. First, let me explain what each of those names mean. GKE stands for Google Kubernetes Engine and is Google's fully managed Kubernetes service. It is the easiest way to run Kubernetes. Within minutes, you can have a production-worthy Kubernetes cluster up and running. Dataproc is Google's fully managed service for running Spark. Dataproc has three flavors. Dataproc on GCE runs on GCE virtual machines using the Hadoop Yarn cluster manager. Dataproc Serverless runs Spark applications without you having to worry about the cluster at all. And Dataproc on GKE runs Spark on Kubernetes, in particular on GKE. If you want all the benefits of Spark on Kubernetes but don't want the overhead of administering it yourself, Dataproc on GKE makes it easy and convenient to use. It is well integrated into the rest of the GCP ecosystem with first-class support for things like Hive Metastore and persistent history servers. And it protects against potential footguns, such as accidentally running a Spark application across multiple zones, incurring cross-zonal network transfer fees. Each Dataproc cluster runs a single version of Spark. Multiple Dataproc clusters can run on a single GKE cluster. These Dataproc clusters may run distinct versions of Spark. Dataproc clusters can, but don't have to, share underlying nodes. All of those combined mean that different versions of Spark can coexist on the same nodes at the same time. Dataproc on GKE does not support the native Spark Submit API. Instead, Spark applications must be submitted as Dataproc jobs. As of now, Dataproc on GKE supports Spark, PySpark, SparkR, and Spark SQL applications. Here's a brief demo showing how Dataproc on GKE works. This demo will show multiple Dataproc on GKE clusters running on the same underlying GKE cluster and run Spark applications on each of them. So, this first command is going to make me a new Dataproc on GKE cluster. It's going to be named Demo Cluster 2.4 because this happens to be running Spark 2.4. It is running in a given region, US Central 1, and I'm pointing at a specific GKE cluster, namely the one named GKE Demo Cluster in the region US Central 1. I'm telling it to install software version Preview 04, and I'm giving it the setup workload identity flag, which will automatically set up all the security for me. I don't have to do any other manipulations of IAM policies. It will correctly set up everything on my behalf. I'm giving it a demo for staging output files, and I'm also telling it what kind of machine I want it to actually run on. In this case, I'm telling it to run on N2 standard 8 machines. I want an auto-scaling group between 1 and 10 of them to be used for all my different forms of computation. This includes my Spark driver, my Spark executor, and any controllers that also have to be run. I also happen to be granting every executor a little over 3 gigabytes of memory, and I'm telling it this is the Spark container that I want it to use. Because this is the Dataproc 1.5 container, this corresponds to Spark 2.4. So we can go ahead and get that started. And just down below, we will see we can set up a watch on that particular Kubernetes namespace, and we can see pods get created as our cluster is being generated. This will take a little bit of time as it's verifying everything, making sure that all of the node pools look correct, and now it's getting to actually installing software inside of the cluster itself. We can see that it started 2 separate pods, the agent and the Spark engine. These are the 2 pods that are always running on a Dataproc and GKE cluster. In total, they take about 0.2 CPU and a little under 200 megabytes of RAM, so quite small. We can see that our cluster creation is now finished and ready to go. So let's try to run a job on it. This is going to be a simple PySpark job. In particular, it's going to be one that's calculating pi. It's only going to be using 10 iterations, so not very many, but you can see that it's pointed at the cluster we just created. You can see almost immediately that the Spark driver pod has been started, and that then it started up the 2 Spark executor pods for it. All of the logs for the Spark driver are being streamed to my console here, as well as being written into cloud storage for further usage. We can see that this happened to calculate that pi is roughly 3.144556. With only 10 iterations, it's not doing a very good job of calculating pi, but it has run the entire thing. We can see that the the Spark executors have gone away, while the driver does continue to be around for a while for looking at logs. In total, this took 19 seconds to run, from 36 seconds to 55 seconds. Now, let's try and make a second cluster, but one that's on Spark 3.1 rather than Spark 2.48. This command is almost identical, except that we have a different name, demo cluster 3.1, and we're giving it a different base Spark image here. Rather than Dataproc 1.5, we're giving it Dataproc 2.0. Dataproc 2.0 corresponds to Spark 3.1. Other than that, it's the same. You can see that the nodes I have it running on are identically set up as before. It's still N2 standard 8s, and there's still 1 to 10 of them for all of our roles. We won't see any manipulations of pods down below because this is happening in a different namespace now. Every Dataproc on GKE cluster exists completely independently in its own namespace. As I just mentioned, the reason this worked is because I created the same node pool twice. All of these node pool values are validated. So I'm going to try to do the same thing, except I'm giving it a new name, demo cluster bad, and importantly, I'm giving it distinct properties. Even though the node pool is still named the same thing, DP, I now have its max set to 5 rather than 10, and I give it a machine type of N2 standard 4 rather than N2 standard 8. This should fail when it actually starts being processed. We can see here that it says exactly that. The requested configuration of node pool DP does not match the existing node pool. Modifications to the request required to match the existing node pool. It needs to change the config machine type from N2 standard 4 to N2 standard 8, and autoscaling max node count from 5 to 10. So it tells me exactly what is wrong so that I can easily fix my request and make it again to make it work. Now, let's run a job on our Spark 3.1 cluster, the one that we named demo cluster 3.1. Rather than just counting Spark Pi, this one is going to figure out the word count of every word in Shakespeare's Macbeth play. Once again, we'll see streaming output from the Spark driver here, and we are not seeing any pods below because it's in a different namespace. If instead we went to the 3.1 namespace, demo cluster 3.1, we would see all of the pods associated with this. Once again, we see a Spark engine and an agent. This would be our driver pod, and we can see 2 executor pods that we caught just as they were finishing. Once again, this finished very quickly. This one looks like it took a little under 17 seconds to run. Thank you. That's an example of how easy it is to use Dataproc on GKE to both create and then use and run Spark applications. Both of these Dataproc and GKE clusters are running on the exact same nodes, so they're completely sharing resources. If I was migrating some number of my jobs from Spark 2.4 to Spark 3.1, this would make it very easy to do the migration because the same resources are used, and whichever job I happen to submit as is where the resources will get used. Dataproc on GKE is currently in beta. It's expected to GA at the end of March 2022. For more information and to sign up for access to the preview, please visit this link. So, what did we learn? Apache Spark is the leading way to do computations over massive data sets. Running Apache Spark on top of Kubernetes allows compute and administrative consolidation and utilizes the de facto standard application environment, Kubernetes. All of this can be done using completely open source tools. But if you want all the benefits of Spark on Kubernetes, but do not want the overhead of administering it yourself, Dataproc on GKE makes it easy, convenient to use without any fear of lock-in. Thank you very much for listening and have a wonderful day.